In this video, we want to look at the concept of Lewis dot structures and the dot structures for covalently bonded molecules. When looking at a molecular dot structure, there are a number of ways to go about the process. The key thing is you're going to want to look at the valence electrons. So the first thing that's easiest to do is to calculate the total number of valence electrons that are in the dot structure. Total number of valence electrons from each atom that makes up the molecule. Having that number will be very important to know the maximum number of electrons that we can use in the dot structure. The next easiest thing, and I think this is more of the puzzle model where you're trying to put it together based like a puzzle, is to connect each atom using a single bond. A bond can be represented as two dots, two electrons being shared between two atoms, or a line. And then we want to complete the octet of electrons around each atom with the remaining valence electrons. Remember, all atoms other than hydrogen are looking to have 8 valence electrons to be stable. Hydrogen will only have 2 because it only has the 1s orbital, which only takes 2 electrons. Now when we're doing this, after drawing the Lewis structure, we can convert each pair of shared electrons to a line. We want to leave unshared pairs of electrons in the diagram. If you run out of the possibility of using single bonds and it's just not possible to make a structure that meets the requirements of the octet rule with single bonds, then we will move on to using double and triple bonds. A double bond involves 4 electrons being shared between 2 atoms, and a triple bond would involve 6 electrons being shared. So let's start with a pretty basic case. We have carbon, which has 4 valence electrons. We have 4 hydrogens, which have 1 electron each. So we have a total of 8 electrons to work with. If you look at carbon, start with the first atom you're given. You have 4 electrons around the carbon. Now we want to put the hydrogen. We have 4 hydrogens, so I'm going to bond 1 to this side, 1 to this side, 1 to this side, and 1 to the fourth side. You'll notice that now I have 8 electrons around carbon, and each hydrogen has 2. So you could just as easily draw each of these pairs of 2 that are shared between 2 atoms as a line. So you could also see this drawn as a carbon with 4 hydrogens around it. Okay, NH3. Nitrogen has 5 electrons, 3 hydrogens for 3 for a total of 8 electrons here. Nitrogen, 2, 1, 1, and 1. So I'm going to put 1 hydrogen on this side, 1 hydrogen down below, and 1 hydrogen on this side. Nitrogen now has 8. Hydrogen each has 2. So you could just as easily write this as a line for each of the bonded pairs. A line with the 2 dots above nitrogen. The 2 dots above nitrogen must stay there because that's an unbonded pair of electrons. H2O. We have 2 hydrogens for a total of 2 electrons. Oxygen was 6. Once again, we have 8. Now, if you look at oxygen, oxygen has 6 valence electrons. So I'm going to put 1 hydrogen on one side and 1 hydrogen on the other. That gives oxygen 8, each hydrogen 2. So you could write it this way. And it doesn't matter which side the 2 hydrogens are on and which side the 2 lone pairs are on. It will determine shape that we look at later, but it doesn't matter for drawing the Lewis structure. SiBr4. Here we have silicon, which has 4 valence electrons, and bromine, which has 7 times 4, 28. So we have a total of 32 electrons to work with. I'll start with the first atom I was given. I'll keep that as my central atom. I know I need bromine. Bromine, you'll notice, has 7 valence electrons. So it has a space for 1 in each bromine. So I'm going to put 1 bromine on this side with its remaining 7 electrons. one bromine on this side with its remaining electrons, one bromine on this side with its remaining electrons, and one bromine on this side. You could also write this Si with 4 lines. Bromines are on the outside, and each bromine's unpaired electrons, the electrons not involved in bonding, must be drawn. So either one of those is fine. You'll notice silicon has 8. Each bromine has 8. Carbon dioxide. Here we have 4 plus 12 for a total of 16 electrons. Now if I start with carbon, it's my central atom, first one listed, bonded to an oxygen, bond this to an oxygen. This does not make a stable atom. I have a stable molecule. I have 6 around this carbon and 7 around each oxygen. There's no other way I could put it together that would get rid of this problem using single bonds. So this is a case where double bonds. We're going to take these 2 electrons and make one double bond, and then we're going to take these 2 electrons and make a second double bond. So carbon will have 4 electrons between it and the oxygen on either side. So here we have a case of a double bond. You could also draw it as 2 lines for the double bond with the 2 lone pairs still shown. So this is a case where we have multiple bonds occurring because there's just no way to put it together using single bonds. Now in the next video, what we will do is look at some more examples of double bonding and some other more complicated cases of Lewis structures.